simulation. So you can think of it as a very simple computer whose memory is a single tape, a one-dimensional tape. It's infinite. So it has we assume that it has the leftmost cell, but it doesn't have the rightmost cell. It goes rightwards or infinitely. And then, so it's something like this. So the tape is divided into cells. Is it better with the light or worse? Okay. And the machine can be in a number of states. There is also a head that moves from cell to cell. At each particular point of time, it points to one cell. And at one step, it can move either to the left or to the right. So it's something like that. For example, or maybe it's better if I give a formal definition first. So a Turing machine consists of states. So Q is a finite set of states. Yeah.
What's the topic of today's lecture? Is it just Turing machines or what?
We're going to introduce Turing machines, single-gate Turing machines, multi-gate Turing machines, then to show that they are in sense equivalent. How can you simulate a multi-gate Turing machine on a single-gate machine? How long does it take to do so? And then we will introduce a number of complexity classes, like P, or P space, and X time. And that's it, more or less. Okay, so we have Q, which is the set of states. We have sigma, that's a finite alphabet. It's input alphabet. Then we also have another alphabet gamma. It's a tape alphabet. So our sigma is a subset of gamma. But gamma contains an additional symbol, contains at least one more symbol than epsilon, and that's the blank symbol. So we have a blank symbol, which is in gamma, but not in sigma. Then we have a transition function, delta. This function takes as input a state from Q and a symbol from gamma, and it maps it to another state, another symbol, and L or R. What it means is this. So this transition function says that if the machine is in one particular state here, and its head looks at a symbol from gamma, then it changes its state to some other state, it replaces that symbol with some other symbol, and it moves either leftwards or rightwards. So, for example, it can be something like delta of Q5, where Q5 is a state, and let's say the symbol is 0. So if you are in state...
Sorry, can you put down the screen of the computer?
I'm not sure if I can put down. I'm not sure. Maybe, is it okay? Or is it better for you?
I don't know. For me, it's great.
And for others?
Okay.
Yeah.
What about the stay movement in?
About what?
Stay movement.
No, we don't have it. It's possible to define a Turing machine so that you have a state movement, which would mean that the head doesn't move, but we won't have it. We will also always have either left or right. So it can be something like delta of Q50 equals, let's say, Q7, 1, L. This means that suppose that the head looks at this cell. Here we have a 0, and the machine is in state Q5. Then what it's going to do next, it's going to do this. It's going to replace 0 by 1. It's going to move leftwards. So now it's going to point to this cell. And the new state is going to be Q7. Yeah.
Do we consider only finite state, only finite sets of states?
Yes.
Okay.
Everything is finite except the tape. So Q is finite, sigma is finite, gamma is finite, and delta is obviously finite. Right. So what else do we have? We have a oh, it's not there. Oh, we have an initial state Q0. So Q0 is from Q. This is the state in which the machine starts its computation. And then we have two other states, Q accept and Q reject. They also come from Q, and they are different. So Q accept is not equal to Q reject. One of them may be equal to Q0, or maybe none of them is equal to Q0. So the machine always, a Turing machine always has at least two states. But usually more. Yeah, maybe I should give an example of some machine. Another problem.
No.
No, okay, I'll try to find one. Okay, so let's say, yeah, maybe I should say also a few words about how the machine computes. It starts in the initial state, Q0. Its head is positioned here on the first cell, on the leftmost cell. It's in Q0. Then the machine takes as input some word. This word is written here in the beginning of the tape. So it can be something like 0, 0, 0. Okay? And then the rest of the tape is empty. It's filled with blank characters. And then the machine computes just following the transition function. If it's in state Q0 and it sees a 0, then it consults its transition function and makes a move. And it stops as soon as it reaches the Q accept or Q reject state. If it finishes in Q accept, then we say that it accepts its input. So the output of the machine is 1. It says yes. That's the word from my language. If it finishes in Q reject, then it rejects the string. So the language of a machine is the set of all strings that it accepts. This is the language decided by a machine. Well, actually, in this course we will be working mainly with machines that always hold on every input. Such machines are called deciders. Sometimes it may happen that you have a machine that can loop forever on some input. In this case, the set of strings that it accepts is said to be recognized by the machine. But if the machine never holds, then we say it decides the language. So there's a small terminological difference between decides and recognizes. But we will be mainly talking about deciders. Okay, so
Sorry, decides means what? Machine called decide if it is.
It holds.
yeah, a machine is decided if it holds on every input.
It
It
can
can never-
take every input.
Yeah, it can never look for error.
Mhm. Okay.
So let me give an example of one such machine. Suppose we work with a single symbol alphabet. So sigma. It contains only one symbol, 0. And we want to define a machine that decides the language that consists of one word, and this one word is 0. So the language decided by machine, so if M is a machine, then L of M is the language decided by a machine. It will be denoted by L of M. And suppose we want it to contain only one word, and this one word contains a single symbol, 0. So how this machine could operate? I will draw kind of a diagram. So this is Q0, it's an initial state. So the machine, the first thing the machine does, it looks at what's in the first cell. And here we can have two options. It's either 0 or blank symbol. So if it's the blank symbol, then at this point we should do what? Well, for example, we can say that we need to write certain rule. So suppose we are in state Q0 and we see the blank symbol. What do you think the machine should do at this point if it wants to recognize this language?
Hold. Reject.
Yeah, it should reject. So in this case, it should really go to the reject state. And then it doesn't have to replace these with anything. So let's keep it like this. And then it has to move somewhere, for example, to the right. Doesn't matter.
What's the language? It's just a set of acceptable words.
Yeah, the language of the machine is the set of words that it accepts. So given 0 as input, it must terminate in the accept state. Given something else as input, it must terminate in reject state. That's the machine that we want to describe. Okay, so in this case, if we are in Q0 and we see the blank symbol, then we go to this state, which is Q reject, and we replace it by itself, and we move right. And then the computation terminates.
Because the machine came to the reject state.
Yes.
Okay.
The computation terminates as soon as the machine enters the reject state or the accept state.
Hmm?
Okay, but now what happens if we see a 0? Delta of Q0, 0. What do you think it should do?
We change our state in some other state, like 1, for example,
Yeah?
and then we not even need to change the symbol, just
Yeah, so
move
just
right.
keep it 0
Yeah,
and move right.
just move right.
Yeah, right. So if we see a 0 like here, then that's fine. The first symbol must be 0. So we just move to another state, Q1. We don't stay in this state because we want to somehow keep in mind that we
We need
saw
to
1
make
0.
1
already.
0, so in the next page just should check
Q1, right.
is it.
And then we move here. So we are in Q1 and now we're pointing here. Good. Now we have another state, Q1. What do we do when we are in Q1?
We check if symbol is just if it's just blank symbol,
Yeah,
then we change our state into to accept,
right,
and if there is 0, then it's to reject.
right. So if it's the blank symbol, then this is the end of our input, and indeed the input consists of a single zero, then we accept it, and we don't have to do anything else. So for example, we keep it as blank and we move to maybe to the left one. Yeah, doesn't matter. And in this case, we immediately enter the reject state because we have seen the second zero. And we don't change it, and we move to the right, for example. So if I want to continue this diagram, it's going to be something like this. So for empty, we're going to queue accept and replace it by empty and move to the left. And if it's 0, then we move to queue reject, replace it by 0, and move to the right. Okay. Is everything clear?
Yes.
So this is the very easy, basic.
And how does the machine looks like? Exact the length of the machine.
Sorry?
Okay, the tape.
Yeah. Well, the tape is just looks like that. It's an infinite tape. Just imagine a
No,
tape like in
of exact this machine.
of exact. Yeah, but the tape itself is always just a tape. It's memory. So initially it's empty. Something happens to it only when you start your machine. Then when you start your machine, you put the input in the beginning. So here, what we had is we ran this machine M on this input. Then initially it was like that, and the head was here, the state was Q0. But then after we read this symbol, we moved here, and we were in state Q1. And then we used this rule, and again we moved here. We entered the reject state, and that's it. So this is the end of the computation on this example, of this machine, on this example. But initially the state of every machine is empty. It's just empty memory.
Okay.
Yeah, okay. What should I say about Turing machines? So Turing machines can, this tape is read-write, so you can read symbols from it, but you can also write symbols on it, to it. Unlike, for example, if you remember finite automata, for finite automata you can't write anything, you just read the input. Here you can modify the tape. You can move to the left and to the right. You don't have to read the entire data. For example, if I had more zeros here, I would still stop. Because I already have 2 zeros. On the other hand, once you've read the content of the tape, you can continue computation and as long as you need. And in principle, the machine can move forever and some kinds of things. Okay. Now let's talk about variants of Turing machines. So this is a single tape Turing machine. There are other variations of a Turing machine. For example, one popular variation is to allow the machine to have several tapes. When it has several tapes, there is only one thing that changes in the definition, and this is the transition function. So what I mean that we can have several tapes. So we can have like 3 tapes, for example. And all these tapes, they have independent heads. So for example, for this tape, the head may be here, or for this one, it may be here, and so on. But the state is the same. It's the same for the entire machine. So the transition function is now defined as follows. It takes, again, one state as input, and a set of symbols. So let's say that we have k tapes. Then the input to the transition function is a state and the k symbols pointed to by the corresponding heads. And all this is are mapped to, again, single state and k symbols. And also you have, for each head you can have a prescription whether it should move left or right. And it's or actually in this case we will allow the state option. So it's like this. Left, right, state where you are. And we have it for each head. So for example, if k equals 3, then we could have something like delta of q5 a 0 c equals q3 a b d l r s. And this would mean that we have something like this. So we have 3 tapes. The state is q5. Here we're looking, for example, here, and we see symbol A. Here we're looking here, and we see 0. And here we're looking here, and we see C. And then, when you apply this rule, it now becomes something like this. The state is q3. So this symbol remains A, but now we move this head to the left, so we point here. The 0 has been changed into B, and we move right, so it's like this. And the C remains C. Oh, no, it doesn't remain C, it becomes D. And we stay here. So this is a multi-tape machine. How it computes? It starts its computation with the input word written on the first tape. And the other tapes are empty, and the heads look at the first cell everywhere. And then they can use these as additional memory. Okay, so there's is everything clear about that? Yeah.
Is it compulsory for all the rest of the tapes to be empty at the very beginning?
Yes. So the input is put on your, so to say, main memory, which is your first tape, and the other memory is empty because you just started your program. So it seems that having more tapes than one is kind of more powerful. And indeed, in terms of computational complexity, it's a little bit more powerful. But in terms of computability, it's not really more powerful in the sense that whatever you can, or whatever language you can decide on a Turing machine with k tapes, you can decide it on a single tape machine as well.
Which problems we solve by this Turing machine? Like examples, some example.
Yeah, any problems. So, I mean, any problems that are solvable by a computer at all. So the idea is that this is a general model of computation. So what's an algorithm? You need a precise definition for an algorithm. And to give a precise definition of an algorithm, you need a certain model of computation. So you need to be precise of what exactly it means to compute. So this Turing machine, it gives you one such option to define what an algorithm is. And then there is a Church-Turing thesis that says that whatever can be computed in principle on any machine can be computed on any machine.
No, you don't understand my question. When we have one types, you give example with one word.
Yeah.
But why we need more types?
More types. Okay.
Yes.
Okay.
Like
So
this. Yes.
right. Okay. A quick example. Suppose you want to recognize palindromes. So yeah. You know what a palindrome is, right? So so you want to be able for such a word to say yes, it's a palindrome. How can you do it with a single tape Turing machine? Well, you look at the first symbol, then you remember that it's A. You remember it by entering into a certain state. Then you go to the end. You see it's also A. Then you somehow mark the symbol. By marking, you can, for example, replace it by something. You can replace it by, like for example, you see this is A, and you enter into QA state. You replace this A by some special symbol, like this one.
You can just erase it, so it will
Well,
be end of the road.
You mean, what do you mean by erasing? You can't really erase anything there. You can replace it by blank symbol.
Yes,
That's
that's
possible.
what I meant.
Yeah, that's this may work in this case. Yes, you can replace it by a blank symbol. We don't need this one, so let's replace it by a blank symbol. And then you are in state QA, and you move until the end of the string. So you, and how do you know when that you are in the end of the string? You know it because here you reach the empty symbol. Then you move one symbol back, and then you see that again it's A, and you say, okay, good, there's a match, and you probably want to replace this by a blank symbol as well, right? And then again you go to the beginning, so you reach this A, you enter into the state QA, and so on, and you go to the end of the string. So how long does it take to recognize a palindrome of size M?
And factorial?
I don't think so.
N square.
N squared, because for each symbol you essentially run the tape twice. Scan the input twice for each symbol, or maybe for each symbol of the first half. So it's going to be N squared. And you can't really do better with a single tape. However, if you have, let's say, 2 tapes, can you do it in linear time?
Yes.
How?
On second tape, we go to the end of the road,
Mm-hmm.
and then just we.
So you mean first you copy this word here, right?
Yes.
And you need off and time to do that. And then here you look at this symbol, here you look at this symbol, and then you move like this.
Yep.
And the symbols must match. So you can do it in linear time. Or another option, you can copy this word backwards to this tape and then match them again.
Mhm.
So as you see, our multi-tape machine gives you, in a way, it gives you more power when it comes to computational complexity.
Sorry, one more question. Does the Turing machine remember what was with it some steps ago, not just the step one step ago?
Well, it remembers only if you store this information somehow.
Uh-huh.
And you can store this information, for example, in the state. So, like here, I said that we see A,
Mhm.
okay? And then we saw A, we enter into a special state called QA. And while we are in QA and the string is not finished, the input string is not finished, we just move right.
Mhm.
Then when we saw this for the first time, then we have to enter into another state, but that state should also have the information that the first symbol that we saw was A. And so on. But we don't need an infinite number of states for that, because at each moment we have to remember what? We have to remember the symbol that we